So this checklist is all about the stopping distance part of the forces topic. And so once again, you need to go through the checklist and identify any areas that you need to work on. So this first question is looking at an experiment to measure reaction time of students. And it says, what is meant by reaction time in this experiment? And in this experiment is important. Generally, reaction time is the time between seeing the stimulus and the response of the action that you take. In this case, the stimulus is, it says, when a green light appeared. So the reaction time is the time between seeing the green light and pressing a key in response. That's what the reaction time is. Boy 2 had an anomalous result in test 2. So we can see here, this is an anomalous result. The others are very much smaller. In this topic on reaction time, it is on page 215 of your revision guide. Now, what you will see is that on a number of occasions, so here you could try and investigate some factors affecting reaction time. You could introduce distractions. Remember to do lots of repeats and calculate the mean reaction time with distractions, which you can compare to the mean reaction time without distractions. The key word here over and over again is about distractions. So nearly always in these mark schemes, the answer is going to be distractions. So why might he have had this anomalous result? Well, and this is not necessary to write this in the answer. The result is larger than the others, so he may have been distracted. And it says, give one conclusion that can be made from the results. So looking at the results of the table, we have to try and make some conclusion looking at the numbers. So we could either look at the numbers, the mean results here, and we see that the boys' results are 0.27 and 0.29, and the girls' results are 0.29 and 0.30. So one conclusion we could make in this experiment is that the boys have a shorter reaction time than the girls. Do not say faster reaction time. Time is not speed. It needs to be shorter or larger. We could also look at it this way. We could have, as we go across the table, we see that the numbers here are going down. Apart from the anomalous value, they're going down, and likewise for these values, they're going down. So that would be one option. The second option would be to say the reaction time decreases with practice. So as we do the exercise more, it gets shorter. Suggest further evidence you could collect to support your conclusion. Well, I did 3 tests with each of the students, so I could do more. So I could do more. Repeats with each person. Okay, I could do that. Or I could do the experiment with more people. the way we say that in general is we could have a larger sample size. It might be that those two boys were particularly quick at reacting, so we couldn't make a general conclusion, so we could do it with more people and see if we still get the same results. Reaction time is an important part at the start of the race, and the table shows the time taken by a boy to run different races. Now, it's important that you notice that here we have one person, so we are no longer talking about different people, 4 different people doing the experiment. Here we're talking about one boy running a race. So in this case, that one person ran 3 different distances: 100 meters, 200 meters, and 800 meters. And these were the times that they got. And it says reaction time is more important in a 100-meter race than in an 800-meter race. Explain why. So if we can think of this, we could imagine, I'm going to make up a number from my table. Imagine the reaction time was 0.25 seconds. Number similar to what was in the table before. Okay? So that means that the first 0.25 seconds was taken up with the reaction time. So here he had 0.25 seconds for the reaction time, plus to actually run the distance, it was 12.49 seconds for the actual race. Here his 0.25 seconds plus he's got 25.38 seconds. And for this last one, 0.25 seconds plus 139.21 seconds. So what we can see is that the reaction time is the same for all the races. So the reaction time is the same for all races. However, it is a smaller proportion of the time, or of the time for the race, when the distance is larger. So as the distance increases, the effect of the reaction time makes up less of the overall time. Therefore, the effect of the reaction time is less when the distance is larger. Or we could say the effect of the reaction time is more when the distance is shorter. So in the last part of this question, it says that 2 girls ran a race, and the figure below shows how the distance changed with time. So this is a distance time graph, but as before, I just check that. First thing I'm going to do is just read what's on the y-axis. Yes, it is distance. Just to be sure that I don't have a velocity time graph, I always do that sanity check. And we need to compare the motion of the 2 runners. Okay. We're looking to compare the motion of the 2 runners, and this is a 6-mark question, so I need to have relevant points written in a coherent way to compare their motion. So normally when I look at a graph like this, I start by looking at some of the key points, the key sections of the graph. So the first thing I can say is both started from the same place. So they're both starting from 0 here. B covered 800 meters. So that point there, it's 800 meters, and that is a time. And to figure out the time, I could draw a line down. And then that's a time down to here, and that is time 126. So B finished at 126 seconds, and we see that A reached 800 meters at this time, which was 160 seconds. Okay, so I've identified some key points on the graph. I can also see this point, which is interesting, and this is where the two lines meet, and I'm just going to find what time that happened at. That was down here, so that time is 114 seconds. So at 114 seconds, the lines cross, which means that one of the runners overtook the other runner, and this is at a distance of 700 meters. So the first thing I do is I look at some of the key points on the graphs. The next thing I'm going to look at then is the sections of the graph and the shape of the graph. So I'm going to look at the shape of the graph. And does that shape change? So what we see is that A, up to about this point here, this is pretty much a straight diagonal line. So this is a constant speed. Whereas we see that at the same time, during this time where A is moving at a constant speed, B starts off with a shallower curve. So this is a lower gradient. So this is a low initial speed. But we can see that the curve, the line is curved. So it's a curved line. So B is accelerating. How do I know? Because the gradient is getting steeper. At this point, then, B overtakes A. Okay, and we can see from here on, B is moving at a high constant speed. Whereas we see that for A, after this point here, the line is curved, so it is acceleration, but it's going to be negative acceleration or deceleration. They are slowing down. Okay, so this is how I analyze the graph. What you can do is then look at some of the main points that you would get from this analysis and put it into a form that makes a coherent argument to allow us to compare the motion of the runners. So this is how I have converted my analysis into my argument in terms of the 6-mark answer. And I've chosen in this case to do it chronologically, so to go through the race from the start to the end, comparing the motion of the runners at each stage. You could do it that way, or you could choose a different way, looking at the main points and then looking at the gradient. However, I think in terms of trying to make a coherent argument, this is probably the easiest for people to follow. I'll just draw your attention to this statement in the question: include data from the figure. So we're going to put in numbers taken from the graph. So it says that I'm going to start at the start of the race. So at the start of the race, I can say that runner A starts at a constant speed, and I measured it get to 440 meters after 60 seconds. So that's the speed they're traveling at, 440 meters in 60 seconds. B, however, starts at a lower speed. I know that because the gradient is lower, so B starts at a lower speed as the gradient is lower. However, B speeds up as the increasing gradient shows. So I mean here that the gradient of this line is increasing, and this shows that B is accelerating. So that's my second mark for that statement. So I've compared the motion of the two runners at the start. Then I can say after 70 seconds, A starts to slow down. So I've picked around about this point. I can see that A's line starts to curve like this. So I've said after 70 seconds, A starts to slow down as the gradient decreases on the gradient of this line. It's decreasing. At 114 seconds, so I've reached this point, B overtakes, and I added in the side here, after 114 seconds and 700 meters, at 700 meters, B overtakes A, as this is where the lines cross. That would be a fourth point. Then I say that A finishes the race at a lower speed, reaching 800 meters after 160 seconds. Again, taking the data from the graph. B won the race, so I'm giving a conclusion to my little paragraph, as she reached 800 meters after only 126 seconds, beating A by 34 seconds. So I've compared the motion of the two runners and I've included data from the graph. And I've tried to do it in a way that is coherent. Now, the next question is about stopping distance. It says a car driver sees the traffic in front is not moving and brakes to stop his car. The stopping distance of a car is the thinking distance plus the braking distance. This statement is really important to remember. Again, if we look in the revision guide, what we can see is that in the page dealing with stopping distance, we can see that that statement is written in larger fonts. It's highlighted by putting it inside a red box. This is clearly a really important statement that will appear in mark schemes, if it's not as it is here given to you in the question. And it asks what is meant by braking distance. Okay, so this has to be an answer about distance. So what is the braking distance? Well, let's take a look at what they say in the mark scheme. So in the mark scheme, they say we've got the braking distance is the distance to stop under the braking force, or once the brakes are applied. So the braking distance, this is the distance travelled after the brakes are applied. And in the textbook, in your revision guide, they use the statement, instead of saying after the brakes applied, they use the expression under braking force. And that's what's in the mark scheme. The braking distance of a car depends on the speed of the car and the braking force. State one other factor that affects braking distance. So here we're thinking of we've hit the brakes, so this is not reaction time. Okay, because this is only about the car and the road. Okay, so there are many things we could have here. We could have factors to do with the car. So to do with the car, we could have worn, we've got the braking force, worn tyres, as that will reduce friction and cause the braking distance to increase. We could have the condition of the brakes. And in terms of then of the road, it could be icy or wet, or weather conditions, the road surface. Are we on a soft road surface like sand, or are we on a tarmac surface? We could have the gradient of the road, that is, are we going up or downhill? And then other factors are things like the load in the car. So that is, how many passengers? So if we have more passengers, more bags in the car, it's going to take longer to stop. How does the braking force needed to stop a car in a particular distance depend on the speed of the car? So, as the speed is increased, the braking distance will increase. So how would we keep the braking distance the same? So note in this question, we want the braking distance to stay the same. So normally we'd say as speed increases, the braking distance increases, but here we want to keep it the same. So how are we going to do that? So as the speed is increased, the braking force must increase to keep the same braking distance. Figure 1 shows the distance time graph for the car in the 10 seconds before the driver applied the brakes. So here we've got the graph. Use figure 1 to calculate the maximum speed the car was travelling at. Show clearly how you work out your answer. So this is a distance time graph. This is not a velocity time graph. So here we need to have the points where the gradient is larger. Remember, speed in a distance time graph is equal to the gradient of the distance time graph. So we need to find where the graph is steepest. So it starts off at this gradient, which is very low, and becomes steeper and steeper and steeper and steeper until it reaches this part. So this is where the gradient is steepest. So what we can do is we can use that between this point and this point and work out the gradient between there to there. So on the x-axis we have the change in time is 10 minus 6 equal to 4 seconds, and on the y-axis we have this distance and this distance, and we can see that we've got 1, 2, 3, 4, 5. So each of these squares is 5. So that distance is going to be 80 meters, and this distance is 170 meters. So the change in distance on the y-axis is 170 minus 80, which is equal to 90 meters. Okay, so the speed is equal to the gradient, and the change in y we had was 90 meters divided by the change in x, which was 4 seconds, which equals 22.5 meters per second. Okay. Then next part, it says the car did not stop in time. It collided with the stationary car and they joined together. So this shows both cars just before and after the collision. It tells us that the momentum of the two cars is conserved. What is meant by this statement? What's meant by this statement is that the total momentum before a collision equals the total momentum after the collision. Total momentum before is equal to the total momentum afterwards. So now we need to calculate the velocity of the two joined cars immediately after the collision. So let me see what information I've got. So I'm going to start with the before case. And again, I start by writing out my numbers. So the mass of the first car was equal to 1,500 kilograms, and the speed of the first car was 8 meters per second, and the mass of the second car was 900 kilometers, and the speed of the second car was 0 meters per second. So now I can work out momentum, and the equation for momentum is that momentum is equal to mass times speed or velocity. So in the case of the first car, I've got the momentum of the first car is equal to m1 times v1, so that equals 1,500 multiplied by 8. And the momentum of the second car is m2 times v2, so that's 900 times 0, so that's going to be 0. And the momentum of the first car was 1,500 multiplied by 8, which is 12,000 meters per second. So I can write down that the total momentum before equals the total momentum after, and that equals 12,000 meters per second. Okay, so that worked out the before case. Now I'm looking at the after case, and in the after case we're told they're stuck together and they're travelling at a certain speed. So the mass afterwards is the two joined together, so that's going to be 1,500 plus 900 kilograms to equal 2,400 kilograms. The speed, we don't know what it is. We do know what the momentum is because that's 12,000 meters per second. We can write our equation. Momentum equals m times v. And I could reorganize this or just simply put the numbers in, which gives me 12,000 is equal to 2,400 times the speed. Therefore, the speed is equal to 12,000 divided by 2,400. Put those numbers into my calculator and I get an answer of 5 meters per second. So the answer is 5 meters per second. Now, question 3. I'm shown an ice skater. Write down the equation that links mass and momentum and velocity. So this is momentum is equal to mass multiplied by velocity. That's an equation that you have to learn off. And we're asked to do this calculation, so we use our usual 4 steps. The velocity is equal to 3.2 meters per second. The momentum is equal to 2,000 meters per second. So, and we're looking for the mass. Okay, so now next step is we write out our equation. And the equation is momentum is equal to mass times velocity. So now I can put my numbers into the equation, which is that 200 meters per second is equal to 3.2 meters per second for the speed multiplied by the mass. So the mass is equal to 200 meters per second divided by 3.2 meters per second. I put that into my calculator and I get an answer of 62.5 kilograms. Now, that's perfectly fine. I will get the marks for that answer. One thing I should notice is that, remember, the rule of thumb is I should have the same number of significant figures. So I really should write this to 2 significant figures with an answer of 63. So that would be the most correct answer to give, but you would get the marks for 62.5. Skater A then bumps into another skater, skater B, who is stationary. They move off together in a straight line. Explain what happens to the velocity of each skater using the idea of the conservation of momentum. So I've got 3 marks, so I need to make 3 relevant points. I would always start this question with by describing what is meant by conservation of momentum. So you can start by saying the total momentum before equals the total momentum after. Okay. Now, before collision, skitter A moving at 3.2 meters per second, and skitter B is stationary, so the total momentum is 200 kilograms meters per second. Don't forget, the question is asking us what happens to the velocity of each skater. Okay. Since the total momentum doesn't change, the velocity of A will decrease. That's as the mass is greater after the collision, because they're stuck together. So because the momentum is the same, it means the velocity will go down. So the velocity of A will decrease, whereas the velocity of B will increase because B wasn't moving at the start. Okay.